portieres. Doubt it. All right, the light is on. That's a miracle. It works every other day. So we have lots of things to cover today, so we can finish this Sturm-Liouville boundary value problems by Friday. So if you remember, I remind you what the eigenvalue problem of interest is, if this thing works. So that's the eigenvalue problem. Try to memorize it because that's a standard form, and if your problem, like in the homework set, doesn't have that form, you may have to put it in that form. And you may have to do some miracles to see if actually it can take that form, but this is our boundary value problem of interest, and what we have shown in the last lecture is that this problem has solutions for certain lambdas, that they are the eigenvalues of the problem, and at least for the problems of interest, lambda were real. They correspond to real eigenfunctions, to one eigenfunction for each lambda. And we also showed that if you take two different lambdas, the corresponding eigenfunctions are orthogonal to each other. And what was the definition of orthogonality for this particular boundary value problem? Can somebody remind me? Functions phi1 and phi2 are orthogonal if what integral is 0? You make me work all the way to come on the back. So integral, yes, of? Times r. That's very important, okay? So basically, this r comes as a weight in the definition of the inner product of the basis functions phi1 and phi2. This is extremely important. All right, so now what today I want to do is the following. I want to actually demonstrate how you can use this basis of the eigenfunctions that you get from solving this homogeneous Sturm-Liouville problem to represent any function. And then, more important, how do you use these eigenfunctions to solve non-homogeneous boundary value problems? So there's a lot of things to cover today, all right? So effectively, we are going to show that if you have a non-homogeneous boundary value problem, so for example, if that thing was not a 0 but some function of x, we will see that using a solution that is a linear combination of the eigenfunctions of the homogeneous problem makes the whole thing very easy, all right? So it's like that's the optimal basis to use, if you can. So let me just give you one example, right? So if you have a function that is piecewise continuous on 0 to 1 and is 0 at the end, you can actually already have seen that you can write it in a signed Fourier expansion given by these nice coefficients. And if you actually want to see this as a Sturm-Liouville problem, you know what? The signs are really the eigenfunctions of this boundary value problem. And you agree with me that this boundary value problem fits in that category, right? Can you see? I mean, if I take p equal to 1 and r equal to 1, immediately I see this problem with essential boundary conditions. So what we did with Fourier expansions, in some sense, it's a little small subset of what we will talk today, all right? So solving this problem, we got signs, okay? Now solving a general problem, who knows what we're going to get? And we are going to try to explore on how to compute solutions in that space. So a few little things, okay? If you write a function, so let me put everything up. So if you expand the function on these eigenfunctions phi of n, and you want to compute the coefficients, look carefully. Will you agree with me that the coefficients are given by this nice formula? And if they are, tell me from where that formula is coming from. Just repeating what we just said a minute ago. So how do you, so you know, if you have a Fourier expansion with sines and cosines, you know how to get the coefficients, right? You use orthogonalities of the sines and cosines. What do we use here to get these CNs? Yep. Say it again. Orthogonality, all right? So if you multiply left and right, let's say with a function phi n, everything on the right-hand side is going to drop, but you have to remember orthogonality is, with respect, it has to involve that R there as a weight in the definition of the inner product. So effectively, the coefficient is the integral of f times phi n times R dx. And what we have taken advantage is the fact that these eigenfunctions are orthogonal, all right? I mean, we proved this in the previous lecture. That's a major thing. So actually, if you want to write this in a standard inner product form, you can write that the coefficient Cm is this L2 inner product between the function f and phi m times R. But in a lot of books, actually, they will write this as an inner product of f with phi m, implying that there is a weight there R, right, that we use for these Sturm-Liouville problems. So again, look at this equation and be sure you understand. If you don't, you ask questions now, all right? It's typical Fourier expansion. The only difference is phi n are the eigenfunctions of the boundary value problem, and the coefficients are the functions are orthogonal, but there is an R involved there. All right, so let me just give you the theorem that I will use today. If you have a function f that satisfies the following two properties, f is piecewise continuous, and f prime is piecewise continuous, and I'm actually not going to say anything about boundary conditions at this point, but if phi n are the eigenfunctions of this homogeneous Sturm-Liouville problem with these boundary conditions, then you can express the function f in this series expansion, infinite series expansion, and you can show that this series converges to f of x if in the neighborhood of x, f is continuous, or it converges 2.5 the value of f on the left and the value of f on the right, exactly as we did with Fourier expansion, okay? As a matter of fact, if you simplify here and you say that f is continuous and only f prime is piecewise continuous, then you don't have to bother about this, and you can show that this thing converges to f of x for all x's, all right? But the theorem says, even if it's piecewise continuous, the same way with Fourier series, it converges to the average of the values on the left and the right, so that's good enough for us. All right, and that's what this theorem repeats. It says here, if f is continuous, then I don't have to bother. Now, let me just say a few things about the boundary conditions. This is extremely important, right? So the homogeneous boundary value problem, all right, satisfies these mixed boundary conditions that involve y and the derivatives of y. So let's take the extreme case first, that we have essential boundary conditions. So y at 0 equal to 0 and y at 1 equal to 0. So in that case, for this expansion to make sense, right, you will anticipate that f at 0 has to be 0 and f at 1 has to be 0. Make sense? I mean, if the eigenfunctions are 0 at the two ends, obviously for this thing to make sense, f has to be 0 at the two ends. But interestingly enough, if you have these very general boundary conditions involving both y and y prime, you really don't have to put any constraints on the function f at the end. So the theorem sort of is very liberal. In the very general case, if you don't have to put any boundary conditions, you don't have to put any constraints on f of x, and this expansion is valid. But again, if you have essential boundary conditions, if you specify the value of y, because then all the phi n's will be satisfying that value, then f of x will make sense to satisfy the same value as phi n of x, okay? So if phi is 0, f has to be 0 for this expansion to actually make a lot of sense. Okay, so let me do one example, starting with something trivial. We're going to expand this function f of x equal to x. Sounds like a ridiculous linear function, but we're going to expand it on the normalized eigenfunctions of this Sturm-Liouville problem with these two boundary conditions. So you notice, because y at 0 equal to 0 goes hand to hand with the function x, right? Because x is 0 at x equal to 0. Can you see that? But I don't really have to impose any constraints on f at the point x equal to 1. All right, so no constraints there. OK. We already have computed the eigenvalues and eigenvectors of this simple Sturm-Liouville problem. This has been our reference problem for the last 2 or 3 lectures. So the eigenfunctions are sine of square root of lambda n times x. And I put a coefficient kn. And where did this kn, this complex kn, coming from? Where did I get that kn? It was in an earlier lecture. We went like fast like that. How do I get that kn? What was the idea? What was the idea? How do we get kn? I mean, I remember everything about sine of square root of lambda n x, right? It's a solution of this, but where is the kn coming? A little bit better, not orthogonality. There is orthogonal, and then there is another word. Orthogonal and orthonormal. So what does that mean? That each of the basis functions has what? Has magnitude. All right? So basically, the integral of phi n times r dx, right, has to be equal to 1. OK? So if you take this with an arbitrary kn, and you multiply with itself, and you multiply with the function r that is 1 here, then, and you do that integral, you get this nice formula. OK? And of course, I am guessing in the derivation, you will have to use the equation that the eigenvalues have to satisfy that maybe, they will come up in, in another slide, but, there was some equation that lambda n has to satisfy. All right, so these are the normalized eigenfunctions. So I can express x directly as this nice function. So it's summation from n equal to 1 to infinity of Cn phi n, where again, notice Cn will be the integral from 0 to 1 of f of x, which is equal to x, times phi n times r times dx. And somebody may say, are you an idiot? Why should I expand x on these complicated functions? Well, because we need to do some examples. All right, we are not going to expand x, but for the purpose of having another lecture, we're going to expand that. All right, so it will take a few minutes, and that's what we need. No, right? So there is the coefficient Cn. So remember Cn. What is Cn here? If I can go back, Cn is the coefficient in the expansion, right? So really what Cn is the projection of f to the eigenfunction phi n. And how do we project? By taking this inner product, but involving r. So if you do this calculation, and you plug in f, which is x, phi n, which is kn times sine of square root of lambda n x, r is equal to 1, and you're good with integrals, and you use this equation for the eigenvalues, all right? There's the answer, all right? So it comes out, no, actually not the answer yet. Okay, Cn is kn times this, and kn from the normalized eigenfunctions is equal to that. And then you have to trust the calculations that the coefficient Cn in the expansion is like that. And you can simplify a little bit. And there is the final answer. I mean, sounds an interesting result, right? So if you want to expand the linear function x in terms of these eigenfunctions, yes, you can do it. Sturm-Liouville, that particular theorem on expanding f of x tells you that you can do it. And you can see the expansion that has these basis functions and these weird coefficients. Now, you know what will be of interest? If I tell you in an exam, for example, prove that this series is equal to x. Don't you think it has to be equal to x? I mean, we started with x, we derived this, but it has to be a unique representation, right? I mean, x, we wrote x with this series. So someone will say this weird series, then it is x. So maybe you want to go backwards to prove it. So how are you going to prove it backwards? that this is X. All right, take a deep breath and think about if somebody asks you to go backwards and prove that this summation is X, and let me know. Okay, a few little things that we already discussed, that these Sturm-Liouville problems, these eigenvalue problems for boundary value problems, they are very similar in nature to the eigenvalue problems we saw in linear algebra AX equal lambda X, right? That have certain solutions only for the eigenvalues, lambda taking particular values, and for each lambda there is an eigenvector. And if you remember, one of the nice things we did, at least for symmetric matrices, using the eigenvectors to express, we use them as a basis vectors, right? That's exactly what we do here. And so someone may be asking if there are similarity between Sturm-Liouville problems and the eigenvalue problems. Is that just simple similarity, or there is much more to it? And the answer is there is way much more. They are both subsets of what is called operator theory, linear operator theory, that would be a fantastic course if you can find anywhere being offered, like in the math department, to take it. I can tell you, I know many universities for engineers, especially double E's, it's a required course. So if you do signal processing and even you do experiments, you need to know about operator theory, which is a subset of functional analysis, and you will see actually an umbrella, a new theory that includes linear algebra and includes, Sturm-Liouville problems and much, much, much more. Okay, so not much more about linear operator theory. So let me, so last time I asked you, you remember the Lagrange identity? Assuming that these functions U and V satisfy certain continuity requirements and the boundary conditions, we proved that for the Sturm-Liouville problem, this is equal to that, all right? And the way we prove it is by doing integration by parts. So let me just formally say, if for any differentiable functions U and V that satisfy the boundary conditions so that you can prove this, then we call the problem to be self-adjoint problem, all right? Usually, if I give you a differential equation with some operator L, all right, in the general case, you're not going to be able to prove that this is equal to that. As a matter of fact, for some problems, this operator L on this second term would be something else. And I gave you homework to actually do integration by parts and calculate the adjoint operator of the operator that I gave you. If it happens to be the same, the problem is called self-adjoint. And I will say most problems, the easy problems that you will hear in all your classes literally are self-adjoint, but a lot of interesting problems in fluids, in electrodynamics, etc., they are not self-adjoint. All right, so lots of interesting problems, unfortunately, don't fit in that category. But just remember, the only way what we did here is we integrated twice by parts, and we had to constrain U and V to satisfy the boundary condition, so everything dropped, and this came equal to that, and we call this problem self-adjoint problem. Okay. All right. So the adjoint operator, so imagine that, let me just go back to this calculation, okay? So when you do this algebra, right, imagine that when you integrate twice by parts, you come with some other operator. Instead of L there, you come with something that doesn't look like L, but is, let's say, L star. That operator is called the adjoint operator. Sometimes the two operators don't come to be the same, but the Lagrange identity is satisfied. All right? So the operator that you will have here to satisfy the Lagrange identity is called the adjoint operator of L. Okay? And for those who like to know more things, for example, students who are going to work in robotics or in control theory, the adjoint operators are fundamental to computing gradients, okay, of functions. And so you will see in optimal control theory, you always work with adjoint operators, okay? So again, if it happens that this operator is the same as that, then the problem is self-adjoint. If not, whatever you get here, assuming the boundary conditions give you a 0, then that is the adjoint operator of M. Yes, integration exactly the same way we did for this example, but whatever operator you get, you call it as the adjoint operator. And by the way, these problems that I mentioned, you know, we work with second order boundary value problems. Obviously, you can extend this to fourth order, and one of the standard problems is if you work with, you know, I wanted to write this as a homework, but when I look at the problem description, it was like a page and a half, and I said to myself, I don't have the energy to write a problem statement that's a page and a half and a solution of 3 pages. And that problem was to do buckling of a column, right, which is a fourth order ordinary differential equation, and you can actually get all the nice eigenmodes for buckling and the eigenvalues. You know, so that may be a wonderful problem for the exam, by the way, okay? Just I give you a lot of things while you're eating turkey to think about. All right. I don't want these things. Let me, I need to keep moving. All right. So let me just say something, right? That up to now, the problems that we actually have worked, we assume that there were such that for each eigenvalue, there was one eigenfunction. Now, there are many problems, unfortunately, that maybe for an eigenvalue, you get more than one eigenfunctions. Did we have this in linear algebra, by the way? Did we have any case in linear algebra where for an eigenvalue, you will get multiple eigenvectors? That sounds familiar somewhere? Yes? So you may ask, with this boundary value problems, what do you need to do to start seeing weird things happening? So here is our standard boundary value problem. But you notice the conditions that I have at the two ends, they are not actually applicable just at x. So let's say the problem is periodic from minus L to L. Notice that each condition involves both values of y at minus L and at L, values of derivative minus L and L. You know what? This is like if you imagine that the problem is one-dimensional, but it's on a string that you bring it together, you merge the two ends. These boundary conditions effectively are periodic boundary conditions. It tells you y at one end should be the y at the other end, and the derivative at one end should be the derivative at the other end. So if you actually try to solve this problem, and there is absolutely nothing new here. If you try to solve it, it comes out that for the interesting eigenvalues that have this nice form, n pi over L squared, you actually get two eigenfunctions. You get cosines and sines. All right? So for these periodic boundary conditions, obviously you're going to get lambda equal to 0 is also an eigenvalue with an eigenfunction equal to 1. But for these eigenvalues, you will get eigenfunctions that involve both cosines and sines. And actually what that means for this particular problem, you know what? You will get your standard Fourier expansion that looks like this. Exactly as we did with Fourier expansions. Okay? So before we expanded the general function, all right, in terms of sines and cosines, now you can actually see that this corresponds to an expansion to the basis functions coming from a Sturm-Liouville problem, but it is a particular Sturm-Liouville problem where the boundary conditions are periodic. Okay? I mean, nothing, you know. So effectively, again, you can see Fourier analysis and the solutions of boundary value problems, again, come hand to hand. All right. I really, I'm going to bypass this. There's really nothing there. Let me see if this is where I want to be. Yes, so this is the place I want to be, okay? So I would like now to do some magic, okay? And the magic goes as follows. We're going to try to solve a non-homogeneous differential equation that has the following form. So if you remember, if L of y was lambda times r times y, that's our homogeneous problem, right? I just put the operator, you remember we define L of y to be this nice thing here, okay? Now, I want to solve the non-homogeneous problem where there is a forcing term f of x. So what I'm going to give you, so we are not lost with algebra, I'm going to give you the simple idea because the rest is really algebra. So the simple idea is if somehow we can solve the homogeneous problem, all right, without f of x, then we should be able to express the solution y to this non-homogeneous problem in a series expansion using the eigenfunctions of the homogeneous problem. And then when you plug in that expansion inside this equation, you should be able to compute the coefficients in that expansion by somehow term by term, right? The same way you expect to do with a power series expansion. Again, we're going to expand y in terms of the eigenfunctions of the homogeneous problem. Now, there is a mu there. There is no lambda, right? So that mu can be a specific number, mu equal to 6. And I have that mu there because you remember the homogeneous problem. Where is my homogeneous problem? The homogeneous problem on the right-hand side doesn't have mu times r times y, has lambda times r times y to remind you that the homogeneous problem has solutions only for particular lambdas, for the eigenvalues, right? So the homogeneous problem has solutions only for particular lambdas. For my non-homogeneous problem, I give you, let's say, m equal to 5. We don't even know if there is a solution, right? But we are going to make an attempt to solve this problem for a given value of mu using the eigenfunctions that we get from the homogeneous problem, okay? So the idea here is we hope that we can easily find the eigenfunctions and eigenvalues of the homogeneous problem. Actually, the technique that I'm going to describe, it is really universal. You can do magic with it if it works for your problem, okay? So pay attention to the details, right? So this is what we want to solve, right? So there is f of x there. My boundary conditions are exactly as before. So just to remove complexity, my boundary conditions are homogeneous. You can easily resolve this, and there is a discussion in one of the slides if this is not 0 there. But right now, my boundary conditions are homogeneous, and I need to deal with that f of x. And there is mu here, and my homogeneous problem has this eigenvalues lambda. All right. So what I'm going to do is I am going to express the solution to the non-homogeneous problem as a series expansion in terms of the eigenfunctions phi n of the homogeneous problem. Can I do that? I mean, obviously here you're going to assume that the solution satisfies some smoothness. Let's say the solution y is continuous. And also, you remember, if it happens that the homogeneous problem gives you solutions 0 at one end and 0 at the other end, then the solution to my original problem needs to satisfy the same things. But in general, right, even if none of those things is satisfied, you can write this expansion, and at least it will converge to some version of phi. Maybe the average of the values on the left and the right side, maybe it would be discontinuous at the ends. But you can expand the actual solution to the non-homogeneous problem in terms of the eigenfunctions of the homogeneous problem. And what are the coefficients? The coefficients are given by this nice formula. But this nice formula is useless. And why is this formula useless? Because we don't know the solution. We don't know what the solution, that's what, we don't know what phi is, so we cannot do this integration to compute the coefficients. So these coefficients have to be computed, you know how? By taking this expansion and plug it inside the differential equation, and then trying to find some equation that will give us b. Okay? And as I said, The algebra, it's not very difficult, and you'll be surprised how powerful this method is to solve any sort of problem that fits in this Sturm-Liouville type scenario. All right, so let me keep going. So this is what we want to solve. So we're going to plug in this inside the differential equation. So I'm going to plug in terms by term. So let's see. These two things there together is L of phi. Phi is my unknown solution. This is what I want to compute. So L of phi, remember L is the operator, right? It's p times first derivative and the whole thing another derivative with minus sign plus q times that function that the operator is applied, all right? So I have L of this summation. Can I write this? Can I go from here to there and tell me what is the big idea that I used to go from this to that? Remember when we work with transformations, linear transformations, what's the idea here that we use? Is linearity of the operator. Thank you. So if you use linearity, you can see you can operate on each phi n with L. And now the magic, L of phi n is equal lambda n times r times phi n. From where is that coming? L operating on the eigenfunction phi n is lambda n times r times phi n. From where is that coming? From the homogeneous problem, it comes because phi n is an eigenfunction, right? And you remember our eigenvalue problem, L phi n equal lambda n times r times phi n. You remember that? From the homogeneous problem. All right, so we are done with this term here, nice. Okay, so let's keep going. This is what we have, this equal to that plus that. Obviously, this we don't know anything yet, okay? So let me do the following. Notice when you write this equation, and again, it's very general, notice there is r of x on the first term, there is r of x on this term, there is no r of x on f of x. If there was an r of x on the last term, you know what I can do? I can cancel it out. So here is the trick. I'm going to write f of x. That's the source term. I'm going to write it as r times f divided by r. And remember, f is a known function, right? It's the source term in my non-homogeneous problem. Guess what the next step will be? What is the next step now? So f, I know f. R, I know r. So I know f over r. What should be the next step to put everything here as a series expansion? What should I do to f over r? What should I do to f over r? Well, I am going to expand it in terms of the eigenfunctions phi n. All right? Why not? I can expand anything. So f over r will be Cn times phi n. And can I compute Cn? Of course, because it's the projection of this function f over r to phi n. So it's f over r times phi n times r dx. R and r cancel. And it comes that this coefficient Cn is the integral of f of x phi n of x dx. Can I compute that? Yes. Do I know f? Yes. Do I know phi n? Yes, because they are the eigenfunctions of my homogeneous problem that I assume I know. So f over r can be written in this wonderful series expansion where the coefficients are known. So you know what? Phi is already in a series expansion. Here I have a series expansion. Here I have r times this series expansion. I'm in business. I'm done. Right? Everything has a series expansion. So for this equation to be valid, what do I need to do? What is the idea? When you have a power series expansion left and right, and it seems all the summations match, what do I need to come up from this? What do we say next? For this to be true, what has to be true? All right, tell me, what has to be true? you know, I'm tired too, okay? Takes a lot of energy. So what has to be true for this to happen? Term by term have to be equal. So you agree that this has to be true then? I am basically taking all the coefficients, right? Look, R will cancel, so the coefficients here will be Bn times lambda n, right? Phi n, forget it, it's, I'm looking for the coefficients of phi n. So I have Bn lambda n, and here I have mu times Bn, so let me see this. Mu times Bn and lambda n times Bn times all the whole thing, phi n equal to 0. So this is what I need to have. I'm done. Because this, you know, do we know Cn? You remember how we computed Cn? By projecting, it was a, you know, the projection of the source term divided by R on the functions phi n. Do I know lambda n? Yes. Mu comes from the differential equation. So I can solve for Bn. And what is Bn? Remind me. What is Bn? I forgot. What is Bn? Bn is the coefficients in, that give me my unknown solution in terms of the eigenfunctions. So if you know Bn, you know everything. All right. So tomorrow put a note and say this lazy professor, he was on a luxury chair and teaching like that. This is unacceptable for Notre Dame standards. This equation looks like that, okay? Now there is a pathology here we need to discuss, right? To compute the coefficient Bn, I am going to have to divide by lambda n minus mu. And you can only divide by a number when that number is not 0. So when are we going to get in trouble, basically? Can somebody tell me, in computing the coefficients Bn, when do I get in trouble? So, and what is m? Is the coefficient in my non-homogeneous differential equation. So when that m happens to be one of the eigenvalues, then this equation, this term here will be 0. And the only way for this equation to be valid is if Cn is 0. And what is Cn? Is the integral of f with phi n. Basically, it's the integral of the source term with the eigenvalue of phi n. So if the source term is basically orthogonal to that eigenvalue, eigenvector, then Cn will be 0, and you have 0 here and 0 there, then that equation is good, and the coefficient Bn cannot be determined. Which means when you write the expansion, the coefficient corresponding to the eigenvalue phi n is going to be undetermined. So you actually have infinite solutions. You can plug in anything and it will work, because that coefficient cannot be determined. Now, if it happens that lambda n is equal to mu, but Cn is not equal to 0, then basically you have no solution at all. Okay? So summary. Here is everything you need to know. And actually, if I can see where my nice theorem is, if there is a theorem, come on. Theorem. OK, here it is. All right. So we are solving this boundary value problem with these conditions. So if mu is not equal to any of the eigenvalues, the solution to the problem is given by this wonderful series. This is the general solution if mu is not equal to the eigenvalue lambda n. Through all problems, right? So, you know, this is a very nice expansion. And what is Cn is the integral from 0 to 1 of f times phi n dx. And that is a big mistake that I need to delete when I go back. So if you see it staying on the slides, email me. All right? So Cn is equal to this integral. And by the way, why there is no r there? What happened to r? Say it again. It canceled because you remember, to get this, we got the expansion of f over r, not of f over r. So f over r times r cancel out. OK? All right. So if mu is not equal to lambda n, this is the very general solution. Now, if it happens that mu is equal to lambda n, two things may happen. Either you have no solution, or you have infinite solutions, okay? And infinite solutions means the coefficient in terms of Pm can be arbitrary, okay? And everything depends if, let me see if I can find it. Yep. Where was that equation? So everything depends if this is going to be 0 or not 0. So if this thing comes to be 0, all right, so if this integral is 0 and mu is one of the eigenvalues, infinite solutions. If mu is one of the eigenvalues and this integral is not 0, then that equation we derive that recursive equation is wrong, and there are no solutions, right? There are no solutions. So you can have, again, one series solution, you can have infinite solutions, or you can have no solution. Does that sound familiar, by the way, with AX equal to B? Actually, if you think of AX equal to B and A, let's say the determinant of A being 0 or non-zero, and you replace it with what I just told you with this integral being 0 or not 0, you actually get the same results. Because when does AX equal to B have a solution? A unique solution, when the determinant is not 0. And when does AX equal to B have infinite solutions or no solution? When the determinant of A is equal to 0, and then other things may be happening regarding B. Exactly the same thing. Is any of this surprising? Obviously not, because all of them are subsets of linear operator theory that generalizes all these ideas. So let's do one little example. It's 11 at 11. Wonderful time. Look at that. 11 at 11, okay? So let me see what example I have for you. So I have this problem. So y double prime plus 2y equal minus x. And we have two nice boundary conditions. They're homogeneous, but one involves y, another one y, and the derivative of y. Now, I have to tell you, and I don't have to tell you really, but you can solve this easily with the methods we learned earlier in the course. This is this analytical solution to this problem. So there is no really need to do any power series expansion, right? But if you want to learn, right, we're going to take an easy problem where we know the answer, and we're going to try to work a power series expansion. But again, whatever we get, the answer is this, all right? So the power series expansion has to be the same, identical to this nice analytical solution. All right. So remember, so I'm going to rewrite this problem as L of y is minus y double prime, all right? It has to fit to my Sturm-Liouville format. And so I'm going to put y double prime on the other side, put x on the left-hand side. So I have minus y double prime equal to y plus x. So immediately you can see that p here is equal to what? How much p is? 1. Q is equal to 0. Mu is equal to how much? How much mu is? 2. R is equal to 1. And f of x equal to x. All right? So again, we don't know that there is a solution which looks nicely like that. So we're going to try to solve this problem by expanding it in the eigenfunctions of the homogeneous problem. And what is the homogeneous problem? What is the homogeneous problem? Can somebody tell me what's the homogeneous problem? The homogeneous eigenvalue problem is y double prime plus lambda times y equal to 0, right? You're not going to say the homogeneous problem is y double prime plus 2y equal to 0. Because 2 may not be even an eigenvalue, may not satisfy, there may not be any y. We need to solve the eigenvalue problem, y double prime plus lambda y equal to 0. This is our mu, all right? And now the homogeneous problem, instead of mu, we're going to have a lambda, where lambda is the eigenvalue. All right, so let's do all of the above. It's just pure algebra. We already know that the eigenfunctions of this are the signs. We had normalized them in an earlier slide. So these are the normalization factors of the eigenfunctions. The eigenvalues that were computed by this equation, it's in an earlier slide. I show you graphically on how you evaluate them. And those are just a reminder. And here's the solution. But for this solution to be true, mu has not to be equal to any of the lambda n's. And if you see here, mu is equal to 2, and none of these numbers is an integer, so we're safe, right? So the solution y is given by this wonderful expansion. Phi n are the signs that we computed. Lambda n are the eigenvalues. And what is Cn is, you remember f of x times phi n dx. So if you plug in here the signs, you can do this integral. You know Cn, you know lambda n, you know phi n, you're done. And I'm going to give you what the answer is. So there is the nice answer. Now, what is the, remember, we do know the actual answer, right? So now we got something very complicated that looks as a series expansion. But, somebody may actually, so this is, believe it or not, this complicated summation, everything here, is equal to this. So obviously, you're not going to do this type of expansions to get solutions that you already know, right? You're going to try to solve problems that don't have closed form solutions. And this Sturm-Liouville type of approach with the series expansion for the solution to the non-homogeneous problem works for any problem. I mean, this, you're not going to be able to get it for me for all problems. I doubt it, because there may not be such a solution, okay? So now, obviously, you may start asking, does this solution actually, does this series solution converges, right? I mean, are there any guarantees? And I think I had a slide, if I can find it. Actually, let me just say, right, and we will come back on Friday, there is a slide that shows you that this series expansion, actually, if you plug in the lambda n's that we computed in an earlier lecture, that they're this, okay? You can see these lambda n's are of the order of n squared, right? So if you actually look at this expansion, you have 1 over lambda n, so you have 1 over n to the power 4. And 1 over n to the power 4 converges rapidly. I mean, after 2 terms, you have the solution. So if you have to program and plot this, you don't have to compute 10 terms. You do compute 2 terms, and that's it. It's done. It converges nicely, okay? All right. So you know what I'm going to do now? Since we have 3 minutes, I am going to solve the transient problem. And I'm going to come back on Friday to repeat this and complete it. But I want to solve the transient problem where, so this is my non-homogeneous transient heat conduction. Remember, this is P of x is the conductivity. And I have 2 source terms, Q times U and F there. But there is a transient term, okay? And so I'm going to try to solve the transient problem. So I remind you the way we solve actually the transient problem with separation of variables. We write the solution U as the solution in space and the solution in time. And when you separate the variables, if you look at the solution for capital X, it comes out to have the very nice form. I'm looking now at the homogeneous part of the problem that you're getting. It comes out that the homogeneous problem in capital X is a Sturm-Liouville problem. Actually, this is how we derived this in the beginning, right? That's the whole idea why we need these Sturm-Liouville problems. So the problem you get for capital X is our standard form with my standard boundary conditions. We already have done this, if not last lecture, 2 lectures ago, right? So we have seen this. So here is what the idea is, okay? I'm going to go fast, and then I'm going to come back to repeat everything on Friday. We're going to expand the solution of the transient problem in terms of the eigenfunctions phi n of x of the homogeneous problem. Of the homogeneous, actually, without any time derivatives, just for capital X. but we're going to make the coefficients Bn of t to be function of time, right? Because we need to solve the transient problem, right? We need to solve the transient problem. So can you guess, when I repeat the algebra that I did before, and I plug it into the transient heat conduction non-homogeneous problem, what type of equation do you think I'm going to get for Bn? Before it was an algebraic equation that iteratively will give me Bn. What do you think now I'm going to get? Guess. Right? Because we're going to plug in this in the differential equation, and the differential equation involves derivative with respect to time. So what do you think I'm going to get when I plug in this and I do the same algebra as before? An ordinary differential equation for Bn. So here is what you actually get. And again, I am going to come back to do this on Friday, but I wanted to show you the answers. So you basically get an ordinary differential equation for Bn that looks Bn prime plus lambda n Bn equal gamma n. And I only want to see somewhere what gamma n is. And here is what gamma n is. And you know gamma n is exactly what I had before for my previous problem. You remember it's the projection of the source term to the eigenfunction phi n. So basically, to compute the transient coefficients, you have to solve an initial value problem. But now you may say, oh, wait a second, the right-hand side I know, but to solve an initial value problem, I need initial conditions. How are you going to find Bn at time 0? What are we going to use to find Bn at time 0? The initial temperature of the problem, right? And how do we find the initial temperature of the problem? Our temperature expansion is Bn times phi n. So if I take this at time 0, the temperature at time 0 is given as f of x. So effectively, the coefficients at time 0, they are nothing else but the coefficients in the expansion of the initial temperature to the eigenfunctions of the homogeneous problem. We're done. So we have initial conditions for this given by these known coefficients Bn, all right? These are the Bn's. We have a forcing term that is known. And do you know how to compute a solution to that problem? Yeah, it's first order ODE with constant coefficients. You can actually compute it right away for me, and that's the answer. And we're done. So you can basically solve now transient boundary value problems like a nonlinear heat conduction. And you expand again on the basis functions of the homogeneous problem. The only difference here is the coefficients Bn have to be functions of time. And as you can see from the final result, you need to compute these coefficients Bn that you compute from the initial conditions. Note the projection there with R. And then you need to compute the forcing term, all right? By the way, this equation does look familiar, doesn't it? For first order ODEs, doesn't it look familiar? It contains the homogeneous solution with right-hand side equal to 0, and then a particular solution that is given by this nice integral. You forgot, okay? All right, so we're done, okay? And so basically, we can solve transient problems. I will repeat this on Friday, spend 5-10 minutes so that, and then what is left is to discuss how to use these methods to compute solutions that blow up, singular solutions. Okay, so we will do part of that on Friday.